All right, by definition, if f is concave upward, what does that tell you about f prime? It's increasing. And it doesn't matter which one of those two things you know first. You know the other. If you know that f is concave upward, you conclude f prime is increasing. If you know f prime is increasing, you conclude f is concave upward. Now, since f prime is increasing, what does that tell you about f double prime? Positive. And again, it doesn't matter which of those you know first. If you know that f prime is increasing, you conclude f double prime is positive. If you know f double prime is positive, go ahead and conclude f prime is increasing. So those three things always go together, don't they? Okay? Then change them around just a bit. If f is concave downward, f prime is decreasing, and f double prime is negative. So everything in black goes together, everything in blue goes together. If you have a critical number where the derivative equals 0, if the derivative equals 0, that means there's a horizontal tangent, correct? So if you have a critical number where the derivative equals 0, but the second derivative is positive, that leads us to a conclusion about relative extreme, about a relative extreme moment. So I forgot what I said now. Derivative equals 0. What did I say the second derivative was? Positive. The second derivative positive means what's the concavity of the function? Up. So we've got concave up. We've got an x-coordinate here that we'll call c, where the derivative equals 0. That means horizontal tangent line. So you put those two things together, and you have a relative minimum. F prime of c equals 0, and f double prime of c positive. F of c is a relative minimum. Question? Who knows what they're going to give you, right? Because we don't have to always know things in a certain order, do we? We can, once we know one thing, we can start figuring out other things. Okay? Now, what happens if f prime of c equals 0, but f double prime of c is negative? If f double prime of c is negative, what's the concavity of that? Down. So it's doing that. And f prime of c equals 0, so there's your x-axis, there's c. That's where our horizontal tangent line is. So now what kind of relative extreme value do we have? Therefore, we could say f of c is a relative maximum. So there's the 5-minute version of what we did today. Any questions? Let's take a look at number 31. So I'm on page 195. The directions for 31 say, find all relative extrema, use the second derivative test where applicable. Now, some of these problems are pretty lengthy. So let's do exactly what the directions say and not more. Okay? Because we're used to them asking us, where the function's increasing or decreasing before they ask us about relative extrema. They don't this time. So we don't need to bother with the first derivative test unless the second derivative test is not practical. And then if it's not, we'll do the first derivative test. But I'm hoping to use the second derivative test. So for number 31, f of x equals x cubed minus 3x squared plus 3. All right, find the derivative. Anytime you're going to find extreme values, you need to find the derivative because you need critical numbers, really no matter which method you're going to use, right? Because except for the end points of closed intervals, the only place extreme values can happen are at critical numbers. So every extrema question needs the critical number. All right, so take the derivative, f prime of x equals 3x squared minus 6x. If I'm going to use the second derivative test, I need the second derivative. So go ahead. Well, I take that back. I went ahead and factored that. Here's where you can go in a different order than me. I'm going to eventually set the derivative equal to 0, right? So either factor it now or factor it later. Doesn't really matter, does it? I'm going to factor it. Doesn't really matter when I do it. Go ahead and take the second derivative. But let me caution you. Use this version of the first derivative. Isn't that version that I underlined easier to find the derivative? Otherwise, I'm using the product rule. Why? Just use the polynomial, 3x squared minus 6x. That way, that double prime is 6x minus 6. And I'm going to go ahead and factor that because that'll be easier if I use the second derivative test. That'll be a little bit easier to figure out if the second derivative is positive or negative. Okay? All right. So, we found the first derivative, we found the second derivative. I still haven't found the critical numbers. In fact, could I have found the critical numbers before I found the second derivative? Sure, right? Again, the order is not the most important thing right now. I tend to do it in this order. First derivative, factor it. Second derivative, factor it. Then critical numbers. There's no rule that says I have to do it in order. I can do first derivative and jump right into critical numbers. I got to do all that. I don't care what order you do it. So critical numbers occur when f prime of x equals 0 or f prime of x does not exist. Since f prime of x is a polynomial, it's 3x squared minus 6x, it always exists. So it's always going to exist. But go ahead and use that factored version. And if you haven't factored it yet, now's the time to factor it and set it equal to 0. So critical numbers occur, in this case, only when 3x times the quantity x minus 2 equals 0. By having it factored, it's very easy to find my critical numbers. What and what? 0 and 2. So x equals 0 and x equals 2 are critical numbers. All right, we've got a table for the first derivative test. We've got a table for the test for concavity. It wouldn't be right if we didn't have a table for the second derivative test. So here's the table I use for the second derivative test. Notice there aren't any intervals. Well, because now possible points of inflection are when f double prime is equal to 0. The critical numbers are still when the first critical is 0 or does not exist. Okay? All right, so second derivative test. First column is C. That's your critical number. Second column is the sine of f double prime of x. And you can, if you want to, you can say sine of f double prime of C. I've done it either way over the years. And then we'll reach a conclusion about our extreme value. So here's what I'm talking about. In the first column, let's put our two critical numbers. In this case, 0 and 2. Now, we're going to use the second derivative. We need to know the sign of the second derivative. Here's why, right? The first derivative equals 0 when x equals 0. horizontal tangent line. The first derivative equals 0 when x equals 2, horizontal tangent line. So what we're trying to decide by using the sign of the second derivative is, does it look like that, where we have a relative max, or does it look like that, where we have a relative min? I know I missed both times, but just pretend that the function and the tangent line touch each other. There. So which is it? We're going to decide. So first, when x equals 0, go back to your second derivative, put a 0 in the factored form. That's why you bothered factoring it. Is the second derivative positive or negative? It's negative, right? 0 minus 1 is a negative 1. 6 times a negative 1 is negative. So, at the critical number, x equals 0, second derivative is negative. Since the second derivative is negative, that means concave down, which means relative maximum. And you can abbreviate that as much as you want to abbreviate it. Rel max. That's fine. All right. Now, at the other critical number, x equals 2. Take 2, put it into your second derivative, the factored form, and tell me, when x equals 2, is the second derivative positive or negative? It's positive. When the first derivative equals 0, and the second derivative is positive, that's a relative minimum. Now, sometimes we forget where things come from. So how do I know those two things? From that we went over a while ago. Okay? So it's one of these things where you need to understand it, and you got to memorize. Otherwise, you got to re-figure it out, every single problem, and that gets old. So, understand it. I think you do. Memorize it. Memorize the way it works. Okay? And I know that in today's educational environment, memorizing is supposed to be a bad thing. I don't know why. Because it's, once you figure something out once, I'd like to be able to use it. Okay, if I learn my way from school to home once, I want to memorize that route so that I can get home from school every day. Don't you? I mean, you really want to get the map out? Every day you're checking the map, you're checking the GPS, you're calling home for direction. No, memorize it. Okay? All right, so what we have then is we have a relative maximum when x equals 0, a relative minimum when x equals 2. The directions said find all relative extrema. We have found where the two occur. We haven't yet found what they are, have we? Okay? So let's figure out what that relative maximum is. So f of 0, or the point 0.03, is a relative maximum. Where did I get the 3? Put it back into the very first equation, back into f. Put a 0 in here, there, well, just those two places, and simplify it. So I found the value of the function when x equals 0. So the relative maximum is actually 3. It occurs when x equals 0. All right? Tell me what the relative minimum is. -1. You put a 2 into your original function, simplify it. So the point 2 -1, or f of 2 equals -1, is a relative minimum. So the actual relative minimum is -1. It occurs when x equals 2. All right, so see what I meant the other day when I said that when the second derivative test works, it's actually pretty easy? You do that a couple times, and you'll get good at that, and that 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 wasn't all that much work. Now, you got to get good at it. You got to practice it enough to get good at it. It won't work. Well, it definitely will not work for critical numbers that you get from here. Because if the first derivative does not exist, neither does the second derivative. And the second derivative has to exist, otherwise we have nothing to put in that column, therefore we can't reach a conclusion. It also doesn't work if your second derivative turns out to equal 0 at one of your critical numbers. Because 0 is not positive, 0 is not negative, so again, we're not able to reach a conclusion. And then as a practical matter, don't use it when it's just so hard to get the second derivative that you're going to screw it up anyway. Okay? So, because I mean, you know, we've worked problems like this, haven't we, where the first derivative was so complicated that the last thing you really want to do is take the derivative of the first derivative. Now, don't use the second derivative then, even if in theory it will work. You know, I mean, let's not be gluttons for punishment, right? We can use the first derivative test to accomplish the same thing. It's just that this is really nice when it works. Okay? So, if I'm working the homework and I get a critical number, let's say I get two critical numbers. One of them is from where the derivative equals 0, and the other one is from where the derivative does not exist. I know the second derivative test will not work for one of my critical numbers. I'm not going to bother with it. I could use the second derivative test for one critical number, the first derivative test for the other. Now I'm doing both tests. I don't want to do both. So whenever I realize that the second derivative test is not going to do everything I need for it to do, I'm not going to bother using it. I'm just not. Okay? And another thing that you got to worry about if you do use it for one of two critical numbers, when you make your intervals on the first derivative test, you still got to make an interval around that other critical number. Well, if you got to do that, why did you bother with the second derivative test? I don't know. I'm telling you not to. Okay? Does that make sense? All right, one more example. We've got to do some graphs. No, the critical numbers are just from the first derivative. Possible points of inflection come from that second derivative. All right, number 46. Still on page 195, it says writing about concepts. So consider a function f such that f prime is decreasing. Sketch graphs of f for A, f prime being negative, and B, f prime being positive. All right. So when they tell us that f prime is decreasing, by definition, what have they told us about the concavity of f? By definition, f is concave downward. So I'm going to write that out. I like thinking f is concave downward better than f prime is decreasing if I'm going to draw a graph. Okay? Now, for part A, we're supposed to sketch a graph. So f is concave downward for part A and for part B. For part A, f prime is negative. All right? If f prime is negative, what do we know about f as far as increasing or decreasing? It's what? Decreasing. So, not only is f concave down, for part A, it's decreasing. All right, and try it out before you do your actual answer if you need to. All right, concave down looks like that. Decreasing, oh, that'd be like this part, wouldn't it? That's concave down and decreasing. That's what our graph needs to look like. concave down and decreasing. So, again, let me show you where everything's coming from. F prime is decreasing means that F is concave down. F prime negative means F is decreasing. So combined, concave down and decreasing. That, talk about F, concave down and decreasing, and it looks something like that. Does it have to look exactly like that? No, I have no idea. I mean, maybe it's, very slowly decreasing. I don't know. But it looks something like what I drew. All right, now, part B. All right, F is still concave downward. F prime decreasing still means that F is concave downward. But F prime is greater than 0 tells us what about F? Is F increasing or decreasing? It's increasing. So F prime greater than 0 tells us F is increasing. So combine what we've highlighted in yellow with what we've highlighted in blue. And again, try it out before you actually draw your graph if you want to on a little scrap of paper. Concave down looks like that. For that concave down, where is the function increasing? For that much of it, right? So the red part is what our graph is supposed to look like. Does that make sense, doing it that way? All right. Any questions on 46? Now, you can betcha that questions like that are going to show up in your future, because that shows me if you understand and really have memorized the facts you're supposed to, and it involves no algebra. So you don't miss it because you accidentally drop a negative off of a number, or you mean to write 1/2 and you accidentally write 1/3. None of that can happen, can it? This is just flat out, do you understand it? Do you have your facts memorized? Mm-hmm. Yep. All right, so these are the two assignments from this section. So the first one is your homework. If you get that one done, you might as well start on the second one. It's all from the same place. Okay?